Welcome. Today I'm going to talk to you guys about inertia and forces. Now we already know a little bit about what a force is, so I'm just going to make some very simple definitions for you here. The idea of a force in physics is about as simple as you can get. It's just any push or pull. Now, of course, you want to be careful about it because a force is, as you might imagine, a vector. I want you to imagine for a moment that you try to push something in no direction. Could you do that? No, you could. Could you try to pull something in no direction? No, you can't. And so we can see right away that it must be a vector quantity. So why did we learn about vectors last unit? Because we're going to have to use them this unit. So hopefully that makes sense. But I think forces are actually an easier way to explore vectors. So hopefully it'll make sense for you here. So this is our first one. Second definition here real quick is mass. And you are totally familiar with this, so I'm not worried. Mass is the amount of matter in an object. You probably use this in chemistry. You could count up the amount of particles that are in an object if you wanted to. But nobody has all day to do that, and so we oftentimes will estimate it. And we'll talk about how we estimate it later on. But for right now, let's just think about mass as being some way of talking about all of the particles that are in an object. So we've got two scenarios here. Let's go with scenario one, or A here. You have a large, very large box, and it's sitting right in the middle of the room. Somebody left it there. It's super annoying. You need to get it out of the way. So what you need to do is to come over to it and apply a force. So I'm going to draw my force vector like that and try to slide it across the room. Now you might already start to think, hey, I've done this before. I know how this works. If that's a really massive box, if there's a lot of mass in that box, then what's going to happen is that it's probably going to have a lot of friction with the floor. And so it's going to be pretty tough to move. So let's take that out of the situation. And so you have this bright idea. That's you with your bright idea. There you go. And you say, okay, I'm going to go ahead and put it on a wheeled cart. And then I'm going to go ahead and push the wheeled cart instead. So same amount of force, now you're just applying it to the wheeled cart. Wheeled carts are used because they have less friction, right? So makes sense. You're taking friction out of the picture. But again, this is still a very massive box. And so my question for you is this. The more massive the box is, what can you tell me about the change in the motion of the object? And hopefully you can see that if you're applying the same amount of force, the more mass that's in this box, the harder it's going to be to get it to move to where you want it to go. And that's because all of the particles that are inside the box resist a change in the motion. And so that brings us to our third definition here. And our third definition is inertia. And it's a weird word. It's weird the way that it's pronounced because the TIA is actually a sh sound. So inertia, right, is the resistance to a change in motion. And it's based on the amount of mass that an object has. The more mass it has, the more it resists a change in motion, and therefore the more inertia it has. You guys totally know this because, as you might imagine, if I keep putting stuff in the box, right? If I keep putting more and more stuff in the box, it's going to be harder and harder for you to push, even with the frictionless wheels that we put on there. So you can still push it, you can still apply the same amount of force, but you're going to get less change in the motion of the box. That's because more mass means more resistance to a change in motion. Hopefully that makes sense. Now up here, and that's all inertia. So up here I have a situation with a kind of a creepy picture that I found on the internet of a situation that I'm very familiar with, and maybe you are too if you've ever ridden a subway. Yeah, subway is like a train, right? So I drew a train out here. And I want you to think about this for a second. If you have a train and the engine is supplying a force forward and ends up providing this speed, or I should say velocity, of 20 meters per second. Wouldn't you agree that if this is you right here, I'll swap out to my red pen. That's you right there. You're standing at this reference point right here. So the Earth doesn't look like it's moving with respect to you, but the train looks like it's moving in this direction at a velocity of 20 meters per second. I think you'd agree that anything inside of the train, unless it was walking or moving itself inside of the train, um, is going along at the same velocity. And so I've drawn out this guy who's standing in the train who also has a velocity of 20 meters per second. That means that all of the particles inside of his body also have a velocity of 20 meters per second. So if we wanted to, we could draw in all of the atoms inside this guy's body and say each one of those atoms is moving forward at 20 meters per second with respect to you standing on the outside. Now, here's what happens. So let's imagine that there's some reason why the conductor for the train or the engineer for the train um, realizes all of a sudden he has to stop. I don't know what sort of emergency it would be, but all of a sudden he realizes he has to stop. So he slams on the brakes. So because the train is all connected together and is solid, the brakes, which are here and here, apply a force to the train directly. And so they get the train to slow down as a result. But what happens to the guy inside? So he's only connected to the train in two places. He's connected to the train by this ring, which is connected by a rope, and the rope, of course, can move. And he's connected to the train by the friction between him and the floor. And so what's going to end up happening is all of the particles in his body, all of these atoms that are all throughout his body, they have that speed or that velocity of 20 meters per second. Is there anything that's going to cause a force to all of these atoms that are in his chest area, let's say, that's going to stop them from moving forward at 20 meters per second when the train brakes? Well, the friction is not going to do it. The ring up here is not going to do it directly. And so what ends up happening is the man, the passenger, and all of the particles in there continue to move forward at 20 meters per second. All of those atoms are doing that, and they will continue to resist a change in their motion because of their inertia. So he moves forward, he moves forward. Now you can see his feet don't move forward, and that's because of the friction. And you're going to see that the ring begins to apply a force. So the ring applies a force to the body that way, and the friction applies a force to the body this way. And between those two, you can see there's a horizontal component right there, and there's a horizontal component right there. And so between those two, and all of the interconnected atoms that are in the body, the force that is applied to the body gets it to stop. Hopefully. If it's not enough force, then the guy falls forward, and so that's a problem. But you've probably felt that in some respects. The same thing happens if you're in a car and the car seat, right? So here's your car seat. Here's you in the car seat, right? And you've got your seatbelt coming across like this, and you're all moving forward at, let's say, some velocity, like so, right? Everything in the car, including you, is moving forward with some velocity. However, when you hit the brakes, right, so there's the brake pedal. When you hit the brakes, the car and the seat, which are all connected together, feel that force to stop. Now, the seat belt is the thing that provides the force to stop. So what do you feel as this guy right here? You feel pushed by the seatbelt to stop because your body and all of the atoms in it want to continue to move forward at the same velocity they had before. That includes the same direction. And so as a result, the seatbelt is the thing that stops you because you're not technically part of the car. It's only the seatbelt that makes you part of the car. That's where you're connected. And that's why seatbelts are there for your safety, right? If you stopped hard enough, your body would continue to go at the same speed it was going or same velocity it was going before. And then you'd have to rely on either the steering wheel or the dashboard or, heaven forbid, the windshield to try to stop you. And so a lot of times in people who get injured in car accidents that don't have seatbelts on, they have trauma to the face or to the chest as a result of the fact that they collided with some other part of the car that was trying to stop them. So in other words, they try as hard as they can to try to move with the same velocity they had before. Again, it's all because of this thing called inertia. Inertia is extremely important, and anything that has mass has inertia. But of course, the more mass something has, the more inertia it has. Think about this just as one last parting thought here. When you are playing around with a toy train and that toy train is coming at you, you shouldn't really be scared because when you apply a force to that toy train, it's pretty easy to stop it. However, if you were playing around in front of a real train, you apply the same force to that real train, it would be very difficult to stop. Not because you're not applying the same amount of force that you had before, but because it has way more mass, which means it has way more inertia, which means it has way more resistance to a change in motion. So it's much harder to change that motion. Okay, I hope that makes sense. Good luck in this unit.